last time I stopped after I explained the hydromechanics in the cochlea, and maybe to just summarize the outcome of that with the two different kinds of forces working together or against each other, how you want to call it, there we get the cochlea working in a way that we have the stiffness of the basilar membrane, which is strong at the beginning and weaker at the end, closer to the apex. And we have more fluid to be moved if the wave goes around the whole path than if it would take a shortcut. And so there would be more inertia for going the long path. And by the forces acting against the acceleration due to the inertia, the propagation of the wave in the fluid is in a way that it takes a shortcut close to the base for higher frequencies, and it goes further back or down the basilar membrane if the frequencies are lower, if it's just a single sinusoidal tone. But if you have complex sounds, then of course the whole mixture will be decomposed into vibrations at different positions, depending on how much content we have at high frequencies and at low frequencies. And along the basilar membrane, we have the sensors then converting the activity, the vibration to neural activity. So that's very short recap from last week, of the end of last week. And now I want to show you a little bit what can be done with, this was the actual demonstrations I will show you are made with already models of the basilar membrane. So we can see some simulated vibrations of the basilar membrane. If we would cut through, maybe I should go back. If you would just look at it with this side view, and we could flip it around so that we have, as we do it usually, we see the low frequencies on the left-hand side and the high frequencies on the right-hand side. This can be done in either way. So I think in this, the next example, we will see it in different ways, so that also the base is stays on the left-hand side. And the first two were made with a model which I will explain later, or start explaining later. At least the first steps of this model I will explain later. And the other models are generated with so-called gamma tone filter banks. And this will be in the next section of the lecture. I will address gamma tone filter banks. And I don't know if we will make it today, because I said before, we will stop a bit earlier and we have some examples of the spatial hearing. There's someone coming. Okay, so I start with the first demo, and this time the sound should come from the speakers. And there's one person now online, just be careful, adjust your volume for the sound. Now it's a 1.5 kilohertz sine wave, might be a bit annoying, the sound, but then you see how the vibration builds up. But maybe I just start it. So when the tone is switched, so this would be the time instance of the vibration at the base, at the oval window. And when the sound tone is switched on, the cochlea builds up some vibration after switching the tone on. We see here the output of the model of the basilar membrane, where again here's the base, and here is the apex on this end. Maybe I can show it with the pointer also for getting it in the recording. Oh no, I have to go here. Here. So this would be the apex, and this would be the base. And here we see the distance from the oval window at the position. And we see that the single tone generates a vibration with a maximum at one specific position. You could remember this. Here, maybe we can see it from the it's a bit below 20 millimeters. So the total length, if the cochlea would be unrolled would be 32 millimeters. And so we see this is somewhat 18 or 19, 18 to 19. Now we just take another frequency, and this would then be a 1 kilohertz tone. Again, single sine wave. Now the frequency is lower, but the vibration is further to the right. And what I did not yet mention is that we see here two curves. The blue is the actual basilar membrane, so it would vibrate, and the red curve just shows the envelope, so to see where the vibration is the strongest. Normally, of course, we see the vibration we see in slow motion because we don't see every 48 thousandths of a second how that vibrates, but just with some frame rate, like it would be visible on a screen. So that's why we see just some snapshots of vibration, and it seems to vibrate slowly, but it would vibrate 1,000 times up and down at every position per second. But let's say how it builds up the vibration is a bit closer to reality, because here it's faded in slowly and so on. So, and we see it's further right, as we would expect it from what I said before. Lower frequencies are further on the right in the vibration. And now a sine sweep, again a bit annoying, maybe. This is very similar, but I took that from the internet. I found this example. And we see the same trend from low to high frequency. And also the vibration is speeding up before it goes to the left-hand side. So we have both effects, the effect of actual vibration with the frequency of the input signal and the position at which the resonance or the maximum vibration builds up. They both are relevant for perceiving, let's say, frequencies. Yeah, and the last example I have here is just pulse trains. So each would be a pulse-like input on the oval window, and we can see what happens then on the basilar membrane. But this is not audible because here we don't have the connection to some frequency. There would be just, each thing would be a click. This is without sound. And there we see that an impulse, it has more or less a flat spectrum, so it should evoke the whole basilar membrane, but it doesn't vibrate at all places at the same time. You see that for each impulse, the vibration builds up here faster, because this would be the higher frequencies, would be seen here, and it is delayed a bit further until the vibration reaches the apex area. From observing this, people call the vibration on the basilar membrane to be a traveling wave. So you will find that, in case you are interested and read some literature, you will find the term traveling wave quite frequently, but in one book, and this sounded logical to me, it was written that this is in fact not what is normally meant by a traveling wave. In a traveling wave, the full energy would be carried in the membrane or in the vibrating thing. But here the energy is carried by both the fluid moving back and forth and the membrane moving up and down. So if there would be no fluid, and if I would have a spring and I would shake it on one end, the wave would travel along this spring and this would then be a real traveling wave. But here it's, as I said before, the effect of both the fluid and the membrane, like this stiff thing which would vibrate. And that's why the term is not quite correct in what is going on in the basilar membrane. And that this was what is noted here, just to make it clear that the energy is at least not only transmitted in the vibration of the basilar membrane, and in fact it's more transmitted by the fluid than in the basilar membrane, because this is fairly light mass in comparison to the fluid. Yeah, and now I want to show you some models of the hydromechanics. And the first models were really electrical circuits, as it's shown here. And these were done, like, I guess, 50 years ago already, so quite long time ago. And there you can find some analogies between mass and inertia on one side, and stiffness of a spring, and also mass of the spring together. And here we see the analogies that we could say the pressure would be represented as a voltage. So we could put some voltage between those two parts, and this would be the potential on this point would be the pressure on the input. That means pressure acting on the oval window. So, and if there would be some pressure, there would be something put into motion. That means it would be accelerated. And if something is moving, then in electrical circuits, this would correspond to the current, which would then flow. And what works against the current to start flowing immediately with full strength would be an inductor. So if you switch on, if you would just have an inductor being connecting here the 2 points, and you switch on the voltage, the current would not jump to a maximum or almost infinity, because it would have no low resistance, but it would start, depending on the inductance, it would start increasing slowly. I hope some of you or most of you have had some lectures about electrical circuits, so that it would make it more motivating maybe to have a look at these examples here. So, and this would be then already one example of one model for the mass being accelerated by the pressure. And then here we have a resonator with an inductor and a capacitor, and some loss with modeled as a resistor, kind of frictions in the vibration or damping in the vibration. And so this would be then the relation of mass and stiffness in the basilar membrane at one point close to the base. And since we can't have a continuous model, we have to split the basilar membrane in short sections, and each section would have to be modeled by the corresponding parameters of the induction and the capacitor and the resistor, so they can be tuned to give a good model. And this would each inductor here would then represent the mass between the two sections, let's say, the mass of the fluid between the two sections. And if we would do that, if we would apply sinusoidal voltage here, there should be at one point the strongest current flowing up and down where the resonance would be located. And if the models are tuned correctly, you can imagine that high frequencies would accelerate less. That means high frequencies don't pass an inductance as easily as low frequencies, as I said before, because the voltage, the current always only starts increasing gradually when there would be a jump at the input. So we have the same effect as with the inertia, that the further we go down, the more easy it is for low frequencies to actually evoke the currents through the whole system, and for higher frequencies it would take the shortcut. And the resonators, of course, have to be tuned accordingly. So then we get this behavior as it would be on the basilar membrane. But in order to get the output, we would have to measure the current going through one of these sections, because that's sometimes not so convenient. People made a kind of a dual system. So you can exchange parts in the model. If you want to measure voltage at some points, like here at each section, you would have to switch conductance and resistance, conductance and resistance. And this would mean that motion would be modeled by the voltage, and the pressure would be modeled by the current. And so if you have the pressure and the voltage is the actual motion, we would have to use a capacitor, because if we switch on a current going through a capacitor, the voltage would start increasing gradually, and vice versa. So the inertia would be then modeled by the capacitor, and the spring mass system would now be a parallel resonator. And instead of putting segments in parallel, you have to put them in series, and vice versa. So that's why you now have the inertia in the sections going up and down from top to the bottom, and the resonators are in the section going along this model. So you can use both. And of course you have to adjust the values of the capacitors and the inductors accordingly. But this would be then the so-called dual system of the system we saw before. And this was then taken later to model that with, let's say, computer simulations. Yeah, now just to complete that, because I will go to the more computer-based or signal processing-based models later with the different models I will address. But now, before I do that, I want to complete and completely show what is coming next when we have this. Again, we have a schematic graph of an unrolled cochlea. I have to repeat it again. That is not possible in reality, but it's just for illustrating. It would be, if it would be unrolled, we would have some vibrations coming here. They would lead to vibrations of the basilar membrane, so it would move up and down, and the fluid would then again vibrate mainly in the first part only for this example, and the oval window would then be pushed out when we have the oval window would be pushed in, the round window membrane would be pushed outside of the cochlea. So, and now the question is what comes next. And for seeing what comes next, we take a cut, like if we would cut through like this, and we would look into the tube along the cochlea, then we would see the cavity. And here I have some graphs showing what this looks like. So it's not just one single membrane for different reasons, but it is a bit more complex what we see here. But the actual basilar membrane would be this part here. Here we see that there's some bony part going in, so which makes the and this bony part could be differently long depending on how far you go on the basilar membrane, because we saw that at the beginning the basilar membrane is quite narrow, and it widens towards the when we get closer to the apex. So there would be less of this bony part, and the membrane would get wider if we go closer to the apex. So we have this basilar membrane, We have another membrane, which is called Reisner's membrane, but this has no effect on the hydromechanics. Yes, a question?
I remember the basilar membrane being bigger not at the apex, but at the exact.
It's I showed it bigger in the side view. Yeah, here I switch back because this here the thickness. This would be the side view. The thickness would be thicker or more, at least more stiff. But if I go back one more slide, and one more slide, and one more slide, this would be the top view, and this shows the gap more or less. And this is more narrow at the beginning, and it gets wider towards the end. So, and here we see just one section. So one position of the basilar membrane at one position of the cross section. And we see here this Reisner's membrane, as I said before, has no mechanical effect. It's more an electrical effect because we have some ions in the fluid which should not distribute in the whole cochlea. So this is more for electrochemical reasons than for mechanical or hydromechanical reasons. And then on the basilar membrane, we have the so-called organ of Corti. And we want to zoom in on that organ of Corti because that's relevant. Here you see some fibers of the auditory nerve, and you see that the auditory nerve is connected to the organ of Corti. So this is then the relevant part for this with the sensors for capturing the vibration and generating neural activities, which would then be collected in the center of the spiral. As I explained before, all the nerve fibers are then bundled in the auditory nerve, and this is in the center of this spiral. And now let's zoom in on that. So here we see what is in the organ of Corti. There are so-called hair cells, and they are called hair cells because they are cells and they have kind of extensions on the top, at least in this view on the top, which look like bundles of hairs. And they are important for these sensors. And now let's see what's going on when the basilar membrane is starting to vibrate. Now the basilar membrane is vibrating here, and we see that there are different effects. For one is that the top part of the organ of Corti, which is called tectorial membrane, is to some of the hairs of the hair cells, it is connected, and because there's some shear between the two, the hairs are moving. They're bending to the left and right and left and right. But also there's some fluid flowing in and out due to this vibration, because there's some compression of a change of the volume of this part here. And also the fluid streaming in and out would also help moving the hairs of the hair cells. And the hair cells have the functions that if they're hairs, they have a scientific name is stereocilia. If they are moving, then there's some neural activity. Or some activity, I must say, more general, which I will explain in a minute. But first, I want to show you a bit more how that in reality looks like, what we just saw here as a sketch. But this is the important thing, and we'll see the hair cells and some models of the hair cells also later. But now I want to show you what that looks like. Maybe just one thing going back. We have the so-called inner hair cells, and we have the so-called outer hair cells. could you imagine why we would say inner or outer hair cells? How can we define inside and outside? Yeah.
There's this canal.
Mhm.
The fluid has to stream in and out. And I mean, the inner hair cells are the last ones to be like touched by this flow of this.
This is one thing, but maybe coming back to the graph before, the whole cochlea is a spiral, right? And the inner hair cells are on the inner side. So the spiral would go around like this. And this is the center of the spiral. And the hair cells which are closer to the center of the spiral, to the axis, let's say, they are the inner hair cells, and the other ones are, it's actually the location within this shape of the cochlea. And here we see the inner hair cells only a little bit here on this graph. Here there would be an inner hair cell. There they have, these are the stereocilia, SC, or the hairs, let's say, of the inner hair cells. So it's now the other way around as I showed it before. And so the axis of the spiral would now be on this side here. And the inner hair cells are closer to the axis. And the outer hair cells are here. Here you see that the hair actual cells are here. And each of them has the stereocilia shape on the top here of the membrane and of this cover here, and they would be normally they're shaped like in a bit of curved or arranged in a curved structure like this. So each of these shapes, U-form shapes, or C in this orientation, C-like shapes would be corresponding to one outer hair cell, and here we don't see the inner hair cell so easily on this view, and but here they are also not that strongly U-shaped, but here you see it a little bit better that they are also shaped like that to some extent. And you see that outer hair cells are in multiple rows, and inner hair cells is in the human auditory system is only one row normally. This is just another electron micrograph where you see the hair cells, the cells, and their stereocilia on top. And just another view on that. And here it's a close look up with the inner hair cell stereocilia. These would be some outer hair cell stereocilia. So you see that what was not so clearly visible, that even one hair cell has not only one row in this U shape, but it has multiples next to each other. And the same would hold for the inner hair cells. From this view, we don't see that easily, but you see that there are some others behind. So they're more next to each other, which is also kind of important, as we'll see later. Yeah, so this will then be explained later in another section, what actually how the inner and outer hair cells react on this bending of their stereocilia. But now this shows what comes next, let's say. But first we want to look a little bit more again to the cochlea and the resonances. Because let's say as engineers, we are somewhat interested also in frequency resolution and time resolution. So we want to get a connection between the position of the resonance of the strongest vibration, let's say, and the frequency to know what's the relation between the two. And for that, we need to introduce some terms. First for the connection of position and frequency. The first term is the characteristic frequency. And the characteristic frequency is defined at the frequency which needs the lowest sound level to be just detected at a specific position. It means if you pick a position, let's say 12 millimeters from the base, and you place kind of a detector there, and you apply different frequencies, and you increase the volume or the strength until you can detect some vibration, then you can imagine that if the resonance is close to that point, you need the lowest amplitude of the input to be detected at this specific position. So it's more or less the point of the highest sensitivity if we start with fairly low sound pressure levels, so that the sound can be detected. So a characteristic frequency represents the points of the highest sensitivity. Maybe you might ask, why do we just need another measure or connection? The second one is called best frequency. And now this is more connected. Here you start with picking a position and then defining the frequency where it's the most sensitive to, for when it goes with relation to the input of the cochlea. And here it's more or less the other way around. You select a frequency, play this frequency with a certain level, and then you look at which position the basilar membrane has the strongest vibration. And in general, you would think, well, it should be the same point, but it's in fact not always the same. So here they measured velocity instead, and not the amplitude of the vibration, but the velocity of the vibration, and the maximum at the specific position. And then the connection of position and frequency would then be in that way that you say the frequency which is actually playing is the best frequency for this specific position where the maximum vibration is happening. But this one depends on the level. So in fact, if in the auditory system, if you increase the sound pressure level of a sinusoidal tone with keeping the frequency constant, the maximum would not be always at the same place. And that's why one thing, this is always at a very low sound level, so at the border of detectability. So this would be always at low levels, and this would be level dependent. So then, of course, with very low levels, the best frequency should come close to the characteristic frequency, but it could shift away a little bit once the level is increasing. But both have, of course, the same tendency that at the base, we have the highest characteristic frequencies and the best frequencies as well. And the same way, at the apex, we have the lowest characteristic frequencies and the best frequencies. And now if we measure the distance from the base to the characteristic or best frequency, we would have to find a mapping. That's what we are interested in. And this is a kind of a nonlinear. So it's not so that, let's say, the frequency in hertz has a linear dependency on the position of the vibration. And that's what we are going to address as well. What kind of measures have been carried out for determining these mappings from position to frequency. But first, I want to give just more or less a quite coarse overview of what it would be like. And if we would take the basilar membrane of a human auditory system, and here it's again illustrated with this spiral shape, and at the base, you would have the highest frequencies. So in this case, I took the graph, they made it for best frequencies. But as I said, the characteristic frequencies would be relatively close at lower sound pressure levels. So at the beginning, there would be the highest frequency which we can perceive, like something like 20,000 hertz. and then the further we go, the lower the best frequency gets, and then at the end we have the lowest frequencies we can perceive with the auditory system. Of course, we can perceive vibrations in air for lower frequencies with our body as kind of vibrations, but then this would be then close to the apex. And if you look at the distance between two frequencies, so for this here it's 200 hertz for this distance, and here if you look at this, it's 13,000 hertz for this distance. So you see that there is there are much more, let's say, frequency, a much wider frequency range, or much higher density, let's say, of frequencies in the area of the beginning at higher frequencies, and if they're getting closer and closer, the closer we go to the apex. And turning this around, you can say the auditory system has a high frequency resolution at low frequencies, and relatively low frequency resolution in the mapping from frequency to location, much lower resolution at high frequencies. That means 1 millimeter would cover a much wider frequency range here than here, in terms of actual frequency difference in hertz along this millimeter, which you might measure. So this again shows us this frequency resolution of the auditory system, and this is also quite important to when we build models of the human auditory system. Then we want to also take that into account. And this can be done by connecting the frequency response and the bandwidth, and this also is reflected in the temporal resolution, as we will see here. So if you want to see time and frequency in one graph, we often calculate a spectrogram of a signal. And for a spectrogram, we use a short time Fourier transform. And then we have to select a frequency resolution and a time resolution of that analysis. But then the frequency resolution is constant for all frequencies. And so here we see that for one voice part, I think this was a part of a speech signal. It's the word head. So this would be the E, I guess. Here we can see the individual spectral lines corresponding to the fundamental frequency and the harmonic components. Because it's a periodic, a quasi-periodic signal, it has integer multiples of the fundamental frequency, or pitch as we call it, also to have spectral components at integer multiples of the fundamental frequency, and we see that here from this graph. And now here we have some measurement of the cochlear vibration, and if you would look at that, we see that here we have the high frequency resolution. So this is only 200 hertz distance between those parts here, and at the higher part we have a lower frequency resolution in comparison to the left graph. But here we see that at high frequencies we have a higher temporal resolution. Here we see even some periodicity in time, while on the lower part we have the individual spectral components, the harmonic components, more separated than in the higher part where the frequency resolution is lower. And I did that again with a gamma tone filter bank model, and generated first with an STFT, a spectrogram of some sound. In this case, I took another signal, and we can hear and see the connection of frequency and time with a spectrogram. And again, people online should be careful, adjust your volume. I will play the sound.
It is always nice to see you. It is always nice to see you. It is always nice to see you. It
I
is
think I showed you
always
this
nice
kind
to
of
see you.
representation
It is
before.
always nice to see you. It is always nice to see you. It is always nice to
You
see
see when
you.
the
It is
pitch is
always
changing,
nice to see
like in
you.
this
It is
part.
always
Wait.
nice to see you. It is always nice to see you. It is always
The
nice
U
to
goes
see
up.
you. It is always nice to see you.
And with the model of
It
the
is always nice to see you. It is always nice to see.
and with the model, with the gamma tone filter bank model, it looks like this.
It is always nice to see you. It is always nice to see you. It is always nice to see you. It is always nice to see you.
So here you can see still quite clearly the individual spectral components at low frequencies, but you see that they are smeared at higher frequencies. You can't resolve them individually anymore. But we still, on the other hand, we see here the temporal, more of the temporal structure in this analysis. And that's kind of one thing which, at least depending on the application, which should be modeled properly.
Is always.
Yeah.
Can you tell me how the cochleogram is measured?
How it is measured? I will explain that when I show how the gamma tone filter bank works. But you can imagine you have a model where you have a filter bank, means that's not only one filter, you have a set of filters which are running in parallel, and you take one snapshot of the amplitude of the vibration, let's say, and then you make one vertical line. As we do it here, if we calculate a spectrogram, we take a short time Fourier transform and calculate the magnitudes, and we plot one column of this picture, and we take the next Fourier transform for a bit shifted input, and then we get the next column of that picture. So that's how we get the 2D graph in a spectrogram. And here we would do it in a similar way, but not using Fourier transform, but actual individual filters which have adjusted frequency and time resolutions, at least to model quite appropriately the basilar membrane vibration. And in order to get closer to the getting the frequency resolution of the auditory system, people measured so-called tuning curves. In this case, this was done for a cat, and they measured the threshold curves when what sound pressure level was required to get the activity of the neurons detecting the vibration. So the neurons normally have some kind of spontaneous firing rates. We'll come to that also later. But at one certain level, you would say, well, now the vibration can be detected. And here you see more or less what would be done if we take one neuron, and we have put different frequencies to the auditory system, in this case the ear of the cat, and then you would need, for example, here with a 1 kilohertz tone, you would need a sound pressure level of about 50 to 60 dB, and the closer you get to this case, maybe something like 3 kilohertz or 4, or it's even close to 5, but yeah, so to the corresponding frequency here, the less sound pressure level you need to detect that vibration in the neural activity. And if the frequency of the tone is higher, you need again much more level in order to be detectable. So what would then be this point for this neuron where the curve has its minimum from the terms I introduced before? Would it be the best frequency or the characteristic frequency rather? Yeah, exactly. So that's basically how the characteristic frequency is defined for a certain position on the basilar membrane, in this case for a position of that neuron which was investigated here, measured. So this would be the characteristic frequency. We will go down from the minimum for that specific location. And the same for others. And now if you look at the graph, it seems like contradictory to what I said before, that the frequency resolution is higher at low frequencies. Here the curves get wider, but this is due to the log frequency scale here. So we have to be careful how we present the results. But what can be seen is that here the curves look almost, or at least similarly wide, I would say, approximately. It means in a certain frequency range, the frequency resolution is almost proportional to the frequency itself. It means if you double the frequency, also the range, the bandwidth, let's say, of the auditory system would be doubled. That would be, because here we are on a log scale. It means the width is then also, if the width stays constant, it would correspond to a linearly increasing with frequency on a linear scale. So that would be one thing, that the width of the curves would increase almost proportionally with frequency, and at lower frequencies apparently not anymore. So it's in the log scale, it's wider. It's still on a linear scale, it still would be more narrow, but on a certain point, they get also would be on a linear scale more or less constant, the width of these curves, which appear getting wider on the log scale. Yeah, and for actually measuring the bandwidth, there are two different concepts in the literature. They came from two different schools of psychoacoustics, as the research topic is called. One was more or less in Munich, and the other one was more in England. And the Munich people, and there's one famous name, is called Zwicker. We have a meeting room here which is named after him. He introduced this concept of how to measure the bandwidth, and he called the bandwidth, which is depending on the frequency itself, as it's not constant over the frequencies. He named that bandwidth critical bandwidth, and he defines the critical bandwidth first quite vaguely as a region in which different frequency components would be processed jointly. That's somewhat a bit vague, because it would not be that within, let's say, if the critical bandwidth would be 100 Hertz, if two tones are 99 Hertz apart, they would be processed fully jointly, and if they're 101 Hertz apart, they would not be completely disjointly processed. So it's kind of a smooth transition still. But the frequency resolution explained as a kind of bandwidth would here then be called critical bandwidth. And I will show you maybe too many examples of how the critical bandwidth was measured, or what experiments have been done to estimate this bandwidth. And also a direct estimation of filter shapes was performed with some of those measurements. And in these experiments, people did, I did not do so much of these explicit experiments, to find out the bandwidth of the auditory system as so-called masking experiments. And you know the term mask more from vision, like if you have a mask on your face, you hide a lot of parts of your face by the mask. You can see some parts, but not the whole face normally. And that's what the term masking means also in in respect to sound. And there are two different terms. One is more qualitative and the other is a bit more quantitative. Is what the term masking means in the auditory system. First definition comes from Acoustical Society of America, and you see here from 1960. Masking is the process by which the threshold of audibility for one sound is raised by the presence of another masking sound. That means if you have one masking sound, that you would increase the audibility of the threshold of audibility for another sound, which would of course be then a lower level sound. But if there would be no mask, the sound would become audible at a certain level. But if you have a mask, it would need a larger level to become audible. We'll see a lot of these experiments later in this semester. Because the masking concept is also very important for audio coding, where we build auditory models for evaluating the masking effect for building good sounding audio coding systems in the ideal case. So this is one definition, and the other one is, as I said, more quantitative. Is masking is the amount by which the threshold of audibility of a sound is raised by the presence of another masking sound. And then you would say in dB, you would say, yeah.
Please.
Yeah. So you could say if the sound of one test signal would normally become audible depending on frequency, it would become audible, for example, at 10 dB. And if you wouldn't have another sound, and this makes the test sound audible only at 30 dB, you would say there's a 20 dB masking, because instead of 10 dB, you need now 30 dB. This is 20 dB more than if there would be no masker. And this is if two sounds are played simultaneously. So maybe you have a question.
Yeah, I just wanted to ask, because what you're saying makes totally sense to me, that I have, let's say there is a certain tone I can only hear if there is nothing else. And if there is a mask sound, I'm not able to hear it. But by reading this last sentence, it would for me, it says more than there is maybe a tone I couldn't hear, but when I hear another masking sound, I now can hear it. So is it raised or is it lowered, the audibility? That's the
threshold of audibility is normally raised, because if there's a loud sound, you would ask people if you want to understand them to speak up, that they would get their parts of their voice which are relevant for understanding would be masked so much that you can't understand them. So they need a higher level to become perceivable to you.
So that so I get it. The threshold itself gets
higher. Yeah, the threshold of audibility is raised. That's what the sentence says here. There are some effects where you, in this case, you shouldn't call it a masking sound anymore, but you can sometimes one sound can help the audibility of another sound. Yeah, but in most cases, one louder sound makes another sound inaudible. And there's one, let's say, I come back to that later, but I want to show it because we need it for the bandwidth of the auditory system. One example where we have a white noise with a certain density level. We have to introduce what density level means. That means that the energy density per frequency, so energy per frequency is then a density level, because if you would have a white noise sound, and if it would not be band limited, the energy would be infinite. So it's always depending on the bandwidth. That's why you speak of a density level rather than of a sound pressure level, because we want to see how much energy is in a certain frequency range. And here we have densities of different levels. That means the higher the density level is, it's also given in dB. So the density of the energy per hertz is then converted to a dB value. And here you see the higher the density, the curve goes up, and I will explain what the curve now means. The curve shows the audibility threshold of single sinusoidal tones in the presence of a white noise signal. And that means if you would, for example, go to the 1 kilohertz tone, which should have a audibility threshold in quiet, there's nothing else, of about 0 dB. And if we have now, just go to one specific point, maybe to this one. If we have a white noise with a density level of 40 dB, the threshold of audibility would go up to 55, let's say. And that means the masking effect is 55 dB. The threshold of audibility of a 1 kilohertz tone is raised by 50 dB. And this is what is shown. When you see masking experiments, you always have to find out what is the signal, what is the masker, and what kind of test signal was used. And here it was, the test signal was a constant, continuous tone, and the masker was a noise, like white noise like signal. Just to show how that might work. I hope my demo works. Yeah.
Like first, every frequency with like white noise spectrum does help the 1 kilohertz tone, or just specific?
It doesn't help it. It prevents it from become audible, because the threshold of this is maybe I didn't say that clearly enough. Here we see so-called masking thresholds, and this is now coming back to this. This line with the 40 is the threshold of audibility of one of the tones with a specific frequency. The threshold of audibility. It means if the 1 kilohertz tone would have 50 dB, which would be quite audible normally, quite loud, but it would be it would be not perceived if we in the same time hear the 40 dB density white noise. That means it doesn't help. It prevents it from becoming audible. It only becomes audible when its level increases above this threshold.
Yeah.
Good that you asked it. Yeah.
Yeah, but the masking definition can.
Yeah.
It shows like we can make some sounds audible.
No. It makes it more inaudible because it raises the threshold of audibility. If you raise the threshold of audibility, that means you need a higher level to become audible. That's what it means. Raising the threshold of audibility means it doesn't raise the level of the sound itself, but if you would not increase the sound, the loudness of the sound or the strength of the sound, you would not hear it. You would need, maybe it's better to, I hope my experiment works, then you might become more clear what it means. Oh, wrong direction.
Yes, if you just tell it in like the simplest terms, the more noise, the harder it gets to hear a certain tone, of course. The more background noise you got. Simple.
Yeah, here now I have a noise. We see this spectrum of the signal, and we have some noise. It's quite a low level, but I can increase the level. Can increase it more here a little. So here we have a masker, which is the white noise, and then I make it down again, and now we have a tone. I made it slowly being switched on and off, because sometimes you can hear better that there's a difference when you hear that there's something being switched on and off. I think all of you can hear it now. So we can find out what would be, of course it's not completely quiet here, but what would be the level of audibility. So that maybe I should turn the plot to not show it again. and turn the plot off so that you can focus on hearing and not detecting from seeing. And now as increase the sound pressure level is not normalized because you can set up the volume differently. And now you can tell me when you hear the tone.
Yeah.
Okay, so somewhat in that range, let's say minus. I still can hear it, but depends on where you're sitting, I guess. Yeah, so but it's somewhat in the range between 25 and 30 dB in this case. Now let's do the same experiment with the noise. Now tell me when you hear the sound, the tone. You can hear it. Okay, and you still could increase the volume of the noise. Now let's see. I think I didn't mention that I can hear it already. Okay, so maybe we have too much noise in the room anyway, so that normally the threshold should be lower, quite a bit lower when you. Even my laptop makes quite some noise. Can somebody hear it already?
Yes.
Okay. Okay, good. Yeah. Also, it works also online.
Maybe try another frequency.
Yeah.
Because I have the feeling that if I heard this tone once for 10 seconds, I can hear it all the time, even if I not hear it.
Yeah. So, oops. So maybe make it a bit to go to the relatively piece part where we are quite sensitive. Something like 3 kilohertz might be a bit annoying, but let's see when you can hear it.
It's audible.
Okay. So again, it was. Can you hear? Some can hear it already. So it's a bit less than 30 dB, so minus 31 or something like that. Now again, the same with maybe put the noise to maximum. Okay, so it was not too much difference. I would have expected more difference.
Sounds like it's like a car going backwards.
Maybe once you have it, you can detect it easier once you have heard it clearly.
But I guess
Yeah, it's audible.
Yep.
I guess the white noise must be actually not as good as the same frequency, right?
Yeah, of course we could also turn up the volume here more, but it might then also get annoying. So, and in a quiet environment, the difference would be of course much larger. So as we see here, depending on what would be the absolute level you are playing, I can't say which density we had now with our setting here. But I think the effect was clear that the sound needs a higher level to become audible. That means I have to turn the volume up more to make the tone audible. And that's basically masking. And what we can see here is that the masking threshold, and that's what we call then the masking threshold, increases after a certain until a certain frequency. It stays more or less constant, and then it increases in this with this log scale frequency and log dB values. It's also converging towards more or less a straightly increasing line. So this is shown here, which would be 10 dB per decade. And this would then mean, again, would show that it's proportional more or less. If you multiply the frequency with a factor of 10, you would have to go up with the level by a factor of 10. So that's kind of proportional, not the level, but the sound pressure. And one explanation of that is that if we have the auditory system analyzes the sound, and we have higher bandwidths at higher frequencies, more of the sound is captured in that band of the white noise. And this means there's more energy in influencing one position of the basilar membrane, because more neighboring frequencies are influencing the vibration of the basilar membrane at higher frequencies than at lower frequencies. So this is an indication that the critical bandwidth, because then the sounds would contribute together to the masking effect within certain bands, which correspond to the bandwidth of the auditory system, so that the bandwidth is larger at high frequencies than at low frequencies, and it would stay almost constant at frequencies below, let's say, 500 Hertz. This is one example of how this frequency resolution would be measured. And in order to get a bit more consistent, and then I will stop for today, the people used not a white noise, but a noise which was somewhat low pass filtered. I took this graph from the literature. I think it's a bit unlucky that they made the graph in this way, because this shows how much the noise was attenuated. That means reduced in the level depending on frequency. So this is the curve A, and this is subtracted from the actual level of the constant intensity of white noise. So actually, when we have a 50 dB, this is called uniform masking noise. If you have a 50 dB density uniform masking noise, its density would be 50 dB until 500 Hertz, and above that, its density would decrease. This curve goes up, but it's subtracted from the intensity density. So that means the actual power spectral density of the sound goes down at higher frequencies. And by this, they tuned this curve in a way that the actual masking thresholds became flat. And I think that's quite relatively logical, that if the density at higher frequencies is lower, the masking effect is also lower in comparison to the white noise. And so this was then done with this kind of shape. And with this shape, you can get better curves over the whole frequency range, because you cover that. And the curves get more or less constant until the place where they almost reach the threshold in quiet. And because of this constants of these curves, the corresponding noise is called uniform masking noise. And with the corresponding masking experiments, they got these curves as they are shown here. And here I wrote, to make it more or less clearly, you weight them by 1 over this function, which is here given in dB, but then in a linear scale, it would be a filter with the frequency response 1 over this. When this curve goes up, then the curve would go down, the noise would go down. Yeah.
Maybe it also makes sense to say, because our human being ear is more sensitive to high frequency, so that's why the level of the tone is lower than lower.
If it's for single tones, the sensitivity of our auditory system is according to this dashed line. So it's not always higher the sensitivity is not always higher for high frequencies. for quite high frequencies, we are quite insensitive. The highest sensitivity we have in the frequency region of 3 to 4 kilohertz, where the threshold of audibility is the lowest. That's more or less where we are the most sensitive. But with masking, this threshold doesn't count anymore, because the audibility threshold of a parallel simultaneously played tone would be constant over frequency. But as I said, the idea behind this for evaluating these experiments would be that the bandwidth of the auditory system increases with frequency. So that means there would be more noise within one band, and the tone always has only one frequency. So there's nothing which increases when you change its frequency. That's why there's more masking in higher frequencies when you have the same density of the noise. So were the first two experiments regarding finding out the bandwidth of the auditory system.
Excuse me, Professor.
Yeah. Yes.
I have a doubt, like while plotting the curves of the sensitivity,
Yes.
like would it trace the this in quiet, or will it be straight line?
I didn't fully understand your question.
Like,
So,
will it have a shape tracing the, like, similar to the threshold in quiet, or will it be like the straight line, like for all the frequencies?
If you have this sound, this uniform masking noise with a certain level, it will be this straight line. For example, for this one, from 50 hertz up to, let's say, 18 kilohertz, it would stay straight, the audibility threshold for this setting when the noise is played at the same in parallel.
So that means that sensitivity part is not considered, right? Like otherwise, from 2 to 5 kilohertz, we have the maximum sensitivity, right?
Exactly. But masking makes this effect void more or less. Only if there is really completely quiet, then we can see this. And the other thing, what we saw in the first lecture was this equal loudness curves. This would also be in quiet if there would be no other sound be played in parallel to a single tone. And you would ask people, how loud do you perceive the sound? There, it would also be still frequency dependent, that sounds in that range would be perceived louder if they have the same sound pressure level than as a tone with for example, 50, let's say 200 hertz. And that was reflected in these equal loudness curves. But this would be if the tone would be played in quiet and no other sound would be present.
I think I got a bit confused with the loudness curve, because I think the loudness curve traces the same.
No. This is really the threshold of audibility of a single tone when there is some other sound present at the same time, which is normally quite a bit louder.
Okay, yeah, thank you. Yeah.
Okay. That's about masking. That's the influence of louder sounds on the audibility of other sounds. But it's good if you ask, because we have more masking experiments, and it's quite important to understand them. And for that, the basic understanding with this threshold of audibility is very important. Yeah, okay. So thanks for asking, and thanks for attending today. And so I will close for now. One more question. Yeah, good.
Like this masking effect is due to the capacity or resolution of our vibration of the membrane, or it's due to the psychological reasons? Like if something is present, we are not.
It's mainly the first, because the basilar membrane is vibrating, and that now it would be vibrating due to the noise, and there would be some other vibration added. But the question is, when do we hear this additional vibration in a already quite strong vibration? So the sensitivity in terms of difference of vibrations would then be what makes the threshold of audibility.
Okay, and like this is for the white noise. If you have like let's say harmonic tone.
Yeah.
So like the equal-loudness curve will not work at that time if some other tone is present. So
we come to that also with masking experiments with harmonic tones and single tones and a narrow band noise and so on. Maybe more masking curves than you would like.